Alright, so here we have the elements of the periodic table. You can see where everything is sorted out. Now you'll see different colors of everything. Anything colored in this sort of yellow orange tone here, these are all non-metals. Okay, so they're not shiny, they don't conduct electricity well, besides carbon. You can see it's all listed out for you here. On the left hand side, middle section here, and then this sort of part here, everything here is a metal. Okay, so if we're looking at properties of how metallic something is, it's more metallic going to the left hand side of the periodic table than it is to go the right. If you go to the right hand side of the periodic table, things become more non-metallic, okay, to use as a word there. So the first thing we're going to look at is the atomic radius. Okay, now before we get on to that, I just want to show you what is the atomic radius. Okay, can everybody see the screen here? Okay, so we have the atomic radius, and it's a really simple definition. Okay, so we know the structure of the atom. Inside the atom we have protons, we have neutrons, and then in the outer shell we have electrons. Okay, so that's the basic definition, or the basic structure of the atom. Here we go, atom. Now, the atomic radius is counting the center point of the atom, so inside the nucleus, that center point there, all the way to this electron here. So this distance that we see here is the atomic radius. Okay, so that's what we have here. That's the definition. Now let's kind of look at the trends of this atomic radius, and then we can go through otherwise. Okay, so if I just go to display properties and trends, just click on this, it will say atomic radius. Click on that. You can see, if we just look at the numbers from left to right, the atomic radius here is 120 pm, which is picometers. That's 10 to the power of minus 12. Very, very small number. And then on this side here, the helium has 140. Okay, so what you can see here is the atomic radius. We'll go a bit further down. We'll start with potassium. You can see that potassium has an atomic radius of 275, and then it sort of gets smaller as we go across the periodic table here. Okay, it does get slightly bigger at some point here, and then it kind of goes back down again like so. So it kind of keeps dropping. Alright, so what's actually happening, or what we can say as a general trend, if we're going across the periodic table, okay, if we're looking at the trend across, as we go to this side of the periodic table, the atomic radius is decreasing. Okay, the reason why it's decreasing is the amount of protons and electrons. So as you go across the periodic table, you're increasing the amount of protons. You're also increasing the amount of electrons. So let's imagine I have my electrons here. If I'm going across, I have more electrons. Remember, electrons are negatively charged. And I also have more protons. Now, if I have more protons, that also means I have more positive charges. Essentially, that means that the center of the nucleus becomes more positive, and the outer rims of the electron shells become more negative. We have a really nice sort of electrostatic attraction. So there's a really strong electrostatic attraction. And that's sort of the thing that's bringing our atomic radius closer towards the center. So that explains why it's decreasing. Now the next one we want to look at is if we go down the periodic table, okay? So if we go down the periodic table, what's happening to our atomic radius? Okay, so if we go down this periodic table here, the atomic radius is, so the atomic radius is increasing. Okay, the reason why it's increasing is every row, so every additional row, you get one additional electron shell. Okay, so imagine I am in group or in row number 2. Row number 2, I have my nucleus, I have 2 electron shells. So that's my atomic radius there. Okay. If I am row number 5, that would mean that I have 5 electron shells to count for. So the atomic radius is counted from the center of the nucleus to the furthest electron shell, or to the furthest position of where the electron is. If I have more rows or have more electron shells, then obviously my atomic radius is going to increase. So that's why the atomic radius increases as we go down the periodic table, because we're adding in new rows of electron shells. Okay, so that kind of explains all that there. Okay, so I'm going to clear this off. Don't forget, don't worry though if you didn't copy it down, because this is recorded. So I'll just clear all that. And the next trend we're going to look at is electronegativity. The other thing I want to just quickly point out why there is an increase or decrease in the atomic radius as you go across. If you actually look at this example we have in the second row here, you will see this number at the top here. That's the atomic number. Okay, the atomic number will tell you the number of protons and the number of electrons you have. So if I have an atomic number of 1, that means I have 1 electron and 1 proton. If I look at boron, it has an atomic number of 5. That means I have 5 protons and 5 electrons. Okay, it also has to do with how many electrons are in the outer shell. So in row 2, remember when we talked about electron configuration, the maximum number of electrons you can have in your second shell is 8, first row is 2, and third row we're saying is 3. Or not 3, 8. Okay, so that's what we have there. Now as we get further across, carbon has 4 valence electrons because it's in group number 4. Nitrogen will have 5 valence electrons because it's in number 5. As we increase this atomic number, we have more protons and we have more electrons. So there's more negative and positive charges to combine with each other there. Okay. Next one we're going to go with is electronegativity. So you can see based on the trend, electronegativity goes down as you go down the periodic table, and it gets higher as you go across the periodic table. Okay, it's called the Pauling scale, so there's no actual unit of measurement for electronegativity. It's more a ratio, if you would like, hence what we mean by the scale. So let's just quickly define what electronegativity is. So the other thing you also see is with the noble gases, they don't really have a electronegativity number. So let me explain firstly what electronegativity is, and that will explain what's happening with these noble gases. Okay, so the definition of electronegativity, and I want to break it down, the concept. Electro obviously meaning by the electrons, and negativity we're talking about is quantity. Now, the basic definition of electronegativity is how willing is the atom to take in more electrons. Okay, that's the basic definition of electronegativity. How willing is my atom going to be to try and take electrons in? Now, I'm going to use two examples. I'm going to use sodium, that is in group 1, so the very far left hand corner of the periodic table, and I'm going to use another element from group 7, which is fluorine. Right, another interesting fact you might want to know, fluorine is actually in your toothpaste. It's the thing that actually keeps your enamel, so basically coating on your teeth, healthy, so it doesn't corrode and break apart. So sodium, if you have a look on the periodic table, it only has one valence electron, okay, because it's in group 1. So if I want to draw sodium, or actually I'll use lithium, same position but a bit smaller. So we have lithium in the center here. It has 2 electrons in this shell here, and then it has another valence electron outside. Okay. We have fluorine, which is in the second row. Its electron configuration is 2,7. Okay. So electron, electron, there. This number here, 7, tells us how many electrons there are in the valence shell. So the most outer shell, we have 7 electrons. So we have 1, 2, 3, 4, 5, 6, 7. And we go like that. Okay. Now, what you actually see with the noble gases is this valence shell here. The valence shell really dictates a lot of things that we need to know. Okay, for anything in group or row number 2, they want a full outer shell. So this is actually a thing we call in chemistry the octave rule. Basically what it means is all atoms want a full valence, in this case outermost valence shell of electrons. Okay, so my question here, if we have a look at lithium, okay, if we have a look at lithium, to get a full valence shell, you need 8 in the second row. So second row, row 2, you need 8 for full outer shell. With fluorine, it's already got 7, so it's a lot easier for it to gain that additional electron than it is to lose 7 electrons and have a full outer shell of 2. If I look at lithium, there's only 1 valence electron here. So if I get rid of this 1 electron, so let's imagine I get rid of this electron here, I've got a full outer shell here. So what that's essentially saying is, for metals like lithium, they rather give the electron away while as non-metals like fluorine would take electrons. Okay, so there's that. I'll just have a look at. Okay, so what we have here is fluorine is really electronegative because it wants to take more electrons in to get a full outer shell. Lithium, on the other hand, wants to lose these electrons to get a full outer shell, so it's very low in electronegativity. So if we look at the trend again, lithium has a electronegativity value of 0.98. Fluorine has a value of 3.98. Fluorine is actually the most electronegative element of the periodic table. So that means it's the element that wants to take in the electrons the most. Now, to answer your question earlier on, Xander, what about these noble gases? Now, the reason why the noble gases don't have an electronegative value is because noble gases have a full outer valence shell. So anything with a full outer valence shell doesn't need to take in any more electrons, hence why they don't have a electronegative value. Okay, hopefully that answers that question there. So there's that. The other thing is I can actually write these out in its ion form. Don't know if you remember ions, but lithium ion, you see how it's lost one electron here? Now, electrons are negative charges. So if I lose a negative charge, I've essentially made this lithium positive, more positive by 1. So lithium is a plus ion. We also call it a cation. Okay, why do I call it a cation? Imagine this bit here. This little t represents positive. That's where the concept of cation is. So it's a positive ion. Here we have fluorine. We've gained an electron. So if we actually gain an electron, we actually make ourselves more negative. So fluorine is actually -1 because we gained a negative charge. That is known as an anion. And that is a negative ion there. Okay? So that kind of concludes what we've been talking about with electronegativity. It's how well does an atom take in electrons? And we've also even talked about ions, cations, and anions, which are negative ions there. Okay? So I'll end the recording here. If you have any questions, you can now ask in the comments below.